how can a ball move upward and still be falling? The answer to that question is that a falling ball is accelerating downward at the acceleration due to gravity, regardless of its current velocity. Recall that a falling ball is one that's experiencing only a single force, its downward weight, and it is accelerating downward in response. The ball's acceleration then dictates how the ball's velocity is changing with time. After all, that's what acceleration is, the rate at which velocity is changing with time. What the falling process doesn't determine is what the ball's velocity was when it started to fall. That's a completely separate issue. When I drop a ball from rest, I'm choosing the initial velocity for the ball to be 0. I let go of it, and for that one moment, I have control over the ball's velocity. I choose it to be 0. After that, the velocity is out of my hands. Literally. From the moment I let go of it, the acceleration due to gravity takes over, and the ball's velocity, which started at 0 by my choice, begins to change with time and become more and more downward, and the ball develops roughly 10 meters per second of downward velocity for every second it's had to fall. But I didn't have to choose an initial velocity of 0. I could choose, for example, to let go of the ball with an initial velocity downward. I can throw it downward like this. In that case, at the moment I let go of the ball and it became a falling object, it already had a large downward velocity. In effect, I gave it a head start on the falling process. But once it left my hand, it accelerated according to the rules of a falling object, and it picked up speed in the downward direction at the usual rate of 10 meters per second, or for the purists, 9.8 meters per second. Well, that leads to another possibility. What if instead of dropping the ball from rest or throwing the ball downward with a downward initial velocity, what if I start the ball with an upward initial velocity? I throw it upward. In that case, it's rising upward, but it's still accelerating downward. It's still a falling ball. And so it continues upward for a while, but as it goes higher and higher, it's being pulled downward and is accelerating downward, and so it's slowing down. It eventually comes to a stop, and then it begins to descend faster and faster and faster. Well, to look a little more carefully at all the properties of a ball that is falling but heading upward, we need some more room. So let's head outside and start throwing a ball around in the open spaces. Before we examine that ball toss carefully, here's a question about the ball's travels. At the moment that the ball reaches the peak height, on its way up, it comes to a peak and then it comes down. Right at that peak, what are its velocity and acceleration? At the peak of its travel, the ball has momentarily come to a stop. Just before that instant, it was heading upward. Just after that instant, it'll be heading downward. So at that point, it is in transition from heading upward to heading downward, and it's doing neither. It's neither rising nor descending. So it's motionless, velocity 0. But that doesn't mean it's not accelerating. Like any falling ball, it's still accelerating downward at the full acceleration due to gravity. So let's return to the ball that I tossed straight up. I'll show it to you again to remind you what it looks like. The basketball took just 2.2 seconds to complete its journey. It spent half that time heading upward and half that time heading downward. To help you see how that movement occurred, I can now begin to play with the video of that basketball toss. The first thing that I'm going to do is I'm going to show you where the basketball was at each moment in time prior to the present. Now, the camera records 30 images per second, so I'm going to have the images of the basketball linger on the screen, each one separated from the next by 1/30th of a second. Here then is that same basketball toss, but with all of the previous basketball images still visible on the screen. That trail of basketball images provides us with enough information to determine the basketball's velocity and position at each frame of the video. Now, I'm going to graph those values, velocity and position, as a function of time. So here it will be the graph of the basketball's velocity versus time and its position versus time. Now, in showing you how they evolve over the course of time, everything happens pretty fast in real life. So I'm going to slow the video down to 1/10 of its normal speed. Here then is the same tossed basketball with its velocity and position graphed as time goes on. The graph of the basketball's velocity versus time is a straight line. We've seen that straight line before. When I dropped the ball from rest, its velocity versus time is another straight line. In that case, the velocity started at 0 when I released the ball and then increased steadily in the downward direction. In this case, the ball started to fall while it was heading upward with a large upward velocity. So it began its fall with a large upward velocity, but it finished its fall with a large downward velocity. And the transition from large upward velocity to large downward velocity was smooth, steady, and seamless. The velocity changed, formed a straight line when plotted against time, as its downward acceleration, the acceleration of a falling object, gradually caused its velocity to shift more and more in the downward direction. The effect of that downward acceleration early on was to slow the rise of the ball. The ball started out, after I threw it upward, with a large upward velocity. So its velocity was upward, but its acceleration was downward. And that causes what we often refer to as deceleration. Acceleration opposite the velocity, so that if you are moving forward but accelerating backward, you slow down. The same thing happened for the ball, the basketball. It was heading upward, velocity was upward, but its acceleration was downward. And it was a constant downward acceleration, so that the velocity in the upward direction gradually decreased, steadily, 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 until at one instant in time, one moment, the velocity was reduced all the way to 0. After that moment, which occurred halfway through the travels, the ball's downward acceleration caused its velocity to become more and more downward. It steadily increased in the downward direction. So the first half of this trip, the upward part of the trip, is the ball having an upward velocity that decreases steadily towards 0. The second half of the trip is the ball dropping from great height, with the velocity that's downward and steadily increasing from 0. Right between these two portions of the motion is an instant in time where the velocity is neither upward nor downward. It's 0. The ball is momentarily motionless, but it's still accelerating there So it continues its transition from velocity upward to velocity downward and shortly returns to my hands. The graph of the ball's position versus time is a smooth arc that curves downward. It starts rising swiftly at first, then arcs over to a flat top, and then arcs downward more and more steeply. That reflects the motion of the ball that starts rising quickly at first, and then more and more slowly as the downward acceleration of the falling ball saps its upward velocity. It momentarily stops rising altogether and then begins to descend faster and faster and faster, covering more and more distance each second. And so we get this rapid rise at first, then slower and slower, then not at all, then slow descent, faster, 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 until down it comes at high speed. The moment at which the basketball reaches peak height is an interesting moment. Up until that point, the ball had an upward velocity that was gradually decreasing, but it was still rising upward to greater and greater height. After that moment of peak height, the ball's velocity was downward and gradually increasing. So the ball was descending away from peak height. That's why the moment of peak height is the moment at which the ball's velocity stops being upward and hasn't yet been downward. It's just hit zero exactly. That's the peak moment. And the ball's motion is remarkably symmetrical around that moment of peak height. If you look at where the ball was 1 second before the moment of peak height and 1 second after the moment of peak height, it's at the same altitude. The ball is the same distance below the peak on both sides of time, 1 second before, 1 second after. Not only that, but the speed of the ball is the same. Before peak height, the speed was directed upward. It was an upward velocity. After peak height, that speed was directed downward. It was a downward velocity, but the speeds were the same. So there's wonderful symmetry around the peak. Because of that symmetry, the rise and fall of a ball looks the same if I play it forward as if I play it backward. You pretty much can't tell the difference between the video of me throwing the ball up and down played forward and played backward. I'll show you. The bottom line here is that a falling ball is falling no matter what its velocity is at the start of the fall. It can start from rest, it can start with me throwing it downward a little bit, or it can start with me throwing it upward. It doesn't matter. Once the ball leaves my hands, the only force acting on it is its weight, and it accelerates downward at the acceleration due to gravity. All the rest, the initial velocity issues, how I start it, are details that we can deal with. So the formulas that I gave previously for a ball dropped from rest still apply. They're still relevant, but we need to spruce them up a little to take into account the possibility that the ball started its fall with an initial velocity that wasn't zero. To take a look at those slightly revised formulas, let's go back to my laboratory. To describe the motion of a falling ball that begins its fall with an initial velocity different from zero, we have to make some modifications to the equations I gave you to describe the motion of a falling ball dropped from rest. We have to incorporate the possibility of an initial velocity that's not zero. So let's look at the ball's acceleration, then its velocity, then its position. Well, the ball's acceleration doesn't change because of any initial velocity. The ball's acceleration has nothing to do with its initial velocity. It's simply the acceleration due to gravity. It's a falling ball. And whether the ball is going up or down or sideways or any which way, as long as the only force acting on it is its weight, it's accelerating downward at the acceleration due to gravity. End of story. So, that was easy. Acceleration's unchanged. Okay, that brings us to velocity. Now, velocity does change. In the old relationship, we had for a ball drop from rest that the velocity at any given time is simply the acceleration due to gravity times the time over which the ball has been falling. That product of the acceleration due to gravity times time, at time zero, at the moment the fall starts, that becomes zero. So the velocity at time zero is zero. Well, if we allow for the possibility of some initial velocity that isn't zero, well, we have to add it in. So at time zero, when the ball hasn't had any time to fall and therefore hasn't undergone any acceleration due to falling, the velocity of the ball is the velocity it started at. So we simply add it in. So the formula that gives us the velocity of a falling ball that started with an initial velocity is the ball's initial velocity plus the acceleration due to gravity times time. That's all there is to it. Finally, that then brings us to the ball's position. This one's a more difficult calculation. First off, we should really allow for the ball to start its fall at a position other than zero. And if we do that, we add in the starting position. So the position at any given later time is equal to the starting position, that's the beginning, plus additional substance. And what is the additional stuff we have to add in there? Well, once again, it's the average velocity of the ball over the course of its fall, from the moment we let it start falling until now, the moment in question. So it's that average velocity times the time between the start of the fall and now. So it's the same product as before, but now the average velocity is more complicated because the velocity didn't start at zero. It started at something else. And if we work through that carefully, and this is simply algebra work, it's not very difficult, but it's enough. I'll leave it out of this video. The final result is that the position of the ball during its fall at any given time where time zero is the moment the fall began, that position is equal to the initial position of the ball, where you let go of it, plus the ball's initial velocity times time, plus 1/2 of the acceleration due to gravity times time squared. So the three terms that are present in that relationship that give you the position of the ball overall. The first term adjusts for the fact that you might want to start the ball's fall at a position other than zero. The second term accounts for the fact that the ball might start with an initial velocity other than zero. And the third term recognizes that a falling ball is accelerating downward at the acceleration due to gravity, and it experiences this evolution in position that goes in proportion to the square of the time, that is, time to the second power. So, whether you care about these quantitative relationships that actually tell you specifically where the ball is in space, how fast it's moving, and what its acceleration is, or whether you simply want to watch the ball fall, its motion is still very simple. The ball starts with its initial velocity, and once it's falling, it accelerates downward. So its velocity is changing in the downward direction. If it's heading upward at a given moment, well, it's becoming less and less upward as time goes on. If it's heading downward, it's becoming more and more downward as time goes on. So it makes use of this velocity then to cover distance, and so you see these rises and falls, or simply falls. They're all dictated by this constant downward acceleration, the downward acceleration of a falling ball. It's time to ask the question I asked you to think about during the introduction to this episode. Suppose I throw a ball straight up. During the time that the ball is above my hand and heading upward, is there a force pushing the ball upward? In answering this question, neglect any effects due to the air. The ball moves upward not because of any force pushing it upward, but because of its own inertia. The ball left my hand with an upward velocity, and even though it begins to fall the moment I stop supporting it, it takes time for that ball's downward acceleration to change the ball's upward velocity into a downward velocity. By now, you should have a pretty good idea how balls move if you drop them from rest or toss them straight up. But most ball sports involve motions of falling balls that are not vertical. If the only thing you could do in baseball or basketball or football or soccer or volleyball was make the ball go straight up and down, those would be pretty dull sports. They still involve falling balls, but those balls have room to move. And in the next part of this episode, we'll take a look at motions that aren't strictly vertical.